So this is going to be section 1.4, and I'm thinking I'll probably break this up into two parts. The first part is going to be discussing the concepts, and then the second part is going to be going through concrete examples. So this section has a good bit of stuff to pack in, so that's why I'm going to break it up into two parts. And the section deals with continuity and one-sided limits. Now, the first topic is continuity at a point, and then continuity on an open interval AB. So before I go into details, what does it mean for a function to be continuous? So imagine this is the x-axis, and we have the y-axis, and then I have a function that looks like the following. And I can keep going like this forever. And notice there's no breaks in the graph. There's no holes. So basically you can draw the graph without lifting your pen or pencil. That's what it means in very simple terms, what a continuous function is going to be. Now, something that's not continuous and let's say I had this following graph, and then I have a hole here, and then I jump to right there. So this graph, there's a jump or there's a hole. So this is something that's not continuous. And so this is a graph that's not continuous, whereas this is a graph that is continuous. Now, when we're talking about being continuous on an open interval, what that means is, let me draw a graph first. Say my graph looks like that. And so this is continuous, and it's continuous everywhere. Now, to be continuous on an open interval is basically taking a segment of the graph. Let's say I wanted to do the segment that goes from where I call A to B. And I use open intervals where at the endpoints, there's going to be holes in the graph. And so if I focus on just that segment, that's going to be a very rough rendition of the segment. And just taking that part, we're going to first talk about what does it mean to be continuous on this. And this is an open interval. AB. So that refers to the x-axis, what interval that is. And I use parentheses because I'm not including the endpoints when I'm talking about an open interval. And this is a picture of a graph where the function is continuous on this particular open interval. All right, so that's what we're going to talk about first. And before I talk about continuous on an open interval, I need to first discuss what it means to be continuous at a single point. So the open interval is going to consist of infinitely many points that have all these points, x values that are inside this interval, they correspond to the graph right here, and they all are supposed to be connected. So I want to talk about what does it mean to be continuous at a single point, single one of these points. So in order to talk about that, first talk about what it means for the function to not be continuous at a single point. And what I drew right here are three cases for which the graph is not continuous at a single point. And we're restricting ourselves to a segment of the graph, and that segment by meaning it's going to be restricted to this open interval a, b. So if I choose some value c in this open interval, like for this one, this is a case where the function's not continuous at this value c. So in blue it says at x equals c, f of c is not defined. The point doesn't exist. There's a hole. So if that hole was closed, then it would exist. So it's not defined at x equals c. The y coordinate of that point doesn't exist. It's not defined. So that's a case where you have not continuous at the value c. You could have it maybe look like this also. So this is another case where it's not continuous. So at c, I have this little jump here in the graph, but yet I do have f of c defined. All right, f of c is defined. It's this closed dot right here. It's not connected around c. And since it's not connected, we say the limit of the function as x approaches c does not exist. And that's because if I look at it from the left side and right side of c, so approaching c from the left side, the graph keeps approaching this hole. Approaching c from the right side, the graph's approaching the closed dot, f of c. So since the left side and right side don't meet at the same value, then that means the limit doesn't exist. All right, so that's the case where you could have f of c defined, but the limit doesn't exist because of this jump, which means that since there's a jump that it's not continuous. And then here's a third case of a function that's not continuous, but I have the limit does exist. So as x approaches c from the left, the graph gets closer and closer to that hole. As I'm approaching c from the right, the graph gets closer and closer to that hole. So the limit exists, but it's still not continuous because there's a hole in the graph where the limit is. And so because of that hole, I jump to where f of c is here, and f of c is defined. It's just right there. So f of c is defined. It's just not equal to the limit. All right, so these are just three cases where you have the function not being continuous at some single point c. So the first one again, so there's f of c is just not defined. That's because there's that hole. And it doesn't jump to anywhere to where it is defined, so it's just a hole. And because of that break in the graph, that means, yeah, it's gonna be discontinuous. And then for this one, this is a case where f of c is defined, but the limit around c doesn't exist because the left side approaches the hole, and then the right side around c approaches the closed dot, which I put as yellow, f of c. This third case is an example where the discontinuous at c, and you have the limit existing, and f of c is defined. It's just that the limit, even though it exists, it's not equal to f of c. So that means if I know these three cases, I can form a definition of what it means for the function to be continuous by taking the opposite meanings of these three cases. If I take the opposite meaning at x equals c, f of c is not defined at c, then we would need f of c to is defined. And then if I take the opposite meaning of this, so d and e means doesn't exist. So the opposite meaning is that the limit does exist. And then the opposite of this statement, where limit exists, but the limit does not equal f of c, well, we would say the limit exists, but the limit does equal f of c. All right, that's taking the negation of these three cases. And that's what it means to be continuous. So a function f of x is continuous at a point for which x equals c when the following three conditions are met. F of c is defined, the limit does exist around c, and further, the limit around c equals f of c. So you have to have all three of these conditions in order to be continuous at a single point. All right, and again, that's just taking these three cases where the limit did not exist, and I took the opposite meanings of those to get the three cases for which the limit does exist, three cases that you need to have. Now the other part is continuous on an open interval. Well, the function's continuous on an open interval basically is continuous at every point in that interval. All right, that makes sense, I think. So if I'm continuous at every single point in the interval, that means I'm continuous on the interval itself. A function that is continuous on the entire number line, and they do as an interval, they put it as negative infinity to positive infinity, is continuous everywhere. All right, so that's the first topic. That's what it means to be continuous at a point, and then continuous on an open interval. Now, when I talked about these cases with discontinuity, like there was a discontinuous case where f of c is not defined, have this hole. This is another case where it's called a discontinuity. And then this case is also another discontinuity at c. For these discontinuities, they can be categorized as removable or non-removable discontinuities. And here are two pictures of examples of removable discontinuities. So for this first one, I just have this hole at C. It's called removable because I can technically think of it as if I had the original graph, and then at C, I just remove this point. And that leaves me with a hole. Sorry, keep messing up. These endpoints need to be open dots. Basically, this closed dot turns into an open dot when I remove it. Okay, so that's a case of removable discontinuity. Here's another example of a removable discontinuity. If I had the original graph, I can redefine it so that it's connected, and I have a closed dot right here, but then let's say I remove it, and in this case, I just move it down to where you see in blue. So it would be like open dot, and then I just moved the dot down. But the original, if I can move the dot back in place, I can connect the graph. So I can think of removable as the graph can be connected. The function can be redefined. So that it's connected at C. These two examples are two examples of non-removable discontinuities. So the first one, there's this break in the graph. So even along with the hole, it jumps. The graph jumps from one segment to the other segment. And so there's not a way that I can redefine it because I would have to physically move the entire graph for one of the segments. This other case is a case where it's non-removable discontinuity, and that's because of a vertical asymptote. So that red dash lines the vertical asymptote, and the graph itself never crosses that dash line. So on the right side of C, the blue portion goes up to positive infinity. On the left side of C, the graph goes down to negative infinity. And since it goes in, it's not connected there, and you can't have it be defined at an asymptote. So that's a non-removable discontinuity. Is due to the vertical asymptote. And the asymptote itself is x equals c. All right, so hopefully these four examples give a clear picture of what's removable versus non-removable. These first two are removable discontinuities. Think of them as like having holes. And if I were to redefine it, I can enclose that hole and then the function will be connected. Same thing for this one. If I enclose that hole, just take the hole that's already existing and just move it to or take the closed dot at F of C and just move it to the hole, and then that makes the graph connected. This one, you have to physically move one whole segment of the graph down or one whole segment of the graph up so you can make them connected. That means it's non-removable since I'd have to do that. This one, it's non-removable because of the vertical asymptote. There's no way I can redefine the function so that it's connected, since by definition of an asymptote, the graph itself is never going to cross that dashed line. And you'll see in the next video where we talk about domain, examples of finding domain. Whenever there's cases with a vertical asymptote, the domain of the function will not include the x value for where the vertical asymptote occurs. All right, so yeah, the next video where I go through examples, some of the examples might ask what's the domain of the function, and we will never include the x value for which the vertical asymptote occurs at as part of the domain. The second topic of the section deals with one-sided limits and continuity on closed interval. And all a one-sided limit is a description of so I think of it as like a one-sided limit is where the graph approaches from one side of the value, from one side of C, and where the graph approaches on the other side of C. So the value for which the graph approaches at one side of C, if it's coming from the right, so let's say if I'm approaching C from the right side, so that's what these arrows mean. I'm approaching C from the right side. The graph keeps getting closer and closer and closer to this point. And that point is what we call, that's going to be L. And this is, if I'm going from C to the right, you would say as X approaches C, but with the plus sign. The plus is just the notation they use to mean approaching C from the right side. So this means approaching C from the right. All right, and that's called a right-hand limit. And then we could have the same thing when it approaches C from the left. And that's called a left side limit. So if I go back to my picture, if I'm approaching C this time from the left side, so that as X approaches C, we use a minus sign above C to mean approaching C from the left. And from our graph, it's getting closer and closer to that same point as which we're approaching from the other side. Which leads me to the next thing, and that's called a left side limit, or left hand limit. The existence of a limit in general, when I like to call the overall limit of f of x is equal to L if and only if the left hand limit equals the right hand limit, which we've seen over and over in examples that I've done from the previous section, or section before that, where I had determining the limit graphically. And we have the limit equals L if the left hand limit equals the right hand limit. And in this case, the overall limit exists. Because they're approaching C from each direction, they're still approaching that same point. So I would say this is limit X approaches C with the minus sign for indicating approaching C from the left side of f of x. That equals L. And then for the other one, I write it as LIM limit, and then approaches C, but this time with the plus sign for approaching from the right. F of x, that also equals L. So since I have these two, that means the overall limit is L. And I've already talked about these two things. I just never had a way of writing it down. So if you're referring to just the left side in which the graph approaches, that's the left-hand limit. And if you talk about where the graph approaches from the right side, that's the right-hand limit. But in order for the overall limit to exist, I need both of those to equal each other. Okay, and we're almost through with the topics. There's this last thing, continuity on a closed interval AB. So all a closed interval is the difference between an open interval and a closed interval is now I include the endpoints of the interval. Whereas I don't include the endpoints for an open interval. So for a function to be continuous on a closed interval, it needs to be first continuous on the open interval. And if it's continuous on the entire open interval, then it needs to be essentially continuous at the endpoints. And in order for it to be continuous at the endpoints, you need the right-hand limit of f of x to equal f of a as x approaches a plus, which means as x approaches a from the right. And then you need the left-hand limit of f of x to equal f of b as x approaches b, and it has this minus sign, meaning x approaches b from the left. And then once it meets those, so I wrote it in mathematical terms, so that is f of x is, and I usually do CONT for continuous on AB with the brackets, meaning it's closed, when f of x is continuous on the open interval with the parentheses. And you have the right-hand limit, x approaches a, equal to f of a, and then the left-hand limit as x approaches b equal to f of b. And really that's just this graph right here is when it's continuous on the closed interval. It's basically connected everywhere and the endpoints are closed. So approaching a from the right side, the graph gets closer and closer to that endpoint, with that endpoint's got a y-coordinate f of a. So this is as x approaches a from the right, so that's where the plus sign comes, f of x, approaches the y-coordinates approach the y-coordinate f of a. Similar if I approach b from the left side, getting closer and closer to that endpoint, the y values are getting closer and closer to f of b. So let's say as x approaches b with the minus sign, approaches b from the left, the f of x values approach f of b. So for not continuous, these are two pictures where it's not continuous. This is one where it's not continuous at the left endpoint a. It's not continuous at the left endpoint, so that's because as the x values are approaching a from the left side, the y values are approaching this hole. And since there's a hole, the value where f of a is this closed dot. They're not approaching that closed dot, so the limit doesn't equal f of a. Now this is a case where it's the other endpoint, the right endpoint. So I'm saying not continuous for the right endpoint. So the right-hand limit doesn't equal f of b. As if I'm the graph as the x values are getting closer and closer to b from the right, the y value is getting closer and closer to that hole. And since it's a hole, it's not defined at that particular value. In fact, it's defined up here with this closed dot. So this is where the limit is. This is where it's defined, where the function f is defined. So the limit doesn't equal where it's defined at b. All right, so that is all of the concepts. The next video, I will jump into examples so we can make use of this abstraction.